All right, so over here, we're trying to solve a first order differential solution to a 3 by 3 Jordan matrix. What does this mean? Well, the question here is given. So solve dz over dt equals jz, with j being this matrix, which is called the Jordan, and z equals z0 at t equals 0. Okay, that's standard. Show that e to the jt equals this solution. So this question turned out to be a lot trickier than I thought when I was going through it, and you'll need to know a lot of different tricks and different properties when doing this equation or just doing this solution. So over here, just for reference, if you want to look these all up, you'll want to probably know the nilpotent shift matrix. This one is pretty easy of a concept. You'll want to know the binomial theorem, or at least what the binomial equation is. You'll want to know first order differential equations, which I hope you know if you're trying to actually watch about this problem. You'll need to know what eigenvalues are. Just as a general knowledge, you don't have to actually know what they are for this problem, but it's good to know like why they exist for this problem. And you'll need to also know what the double summation trick is. And I'll get into all of these later, but this is, again, just for reference if you want to look these up later. So, how do you find the solution to this problem? Well, over here, let's just go to the general solution and show why it exists and what we're supposed to be looking for. So, a first order differential equation, it's very common to use this solution over here, which is x equals some initial value to the e to the kt. Actually, it's almost standard to always use this value. And why is this? Well, you can verify over here. By plugging this, this value into the derivative, you'll get back this, which is exactly kx. So you're going to be getting back your solution. All right, so from this, we can tell that first over here, k is scalar, which is an eigenvalue. This is actually very important, knowing that k is an eigenvalue, because you're not going to be getting this with other kinds of terms. So what we're going to be looking for are eigenvalue solutions. What are eigenvalues exactly? So eigenvalues are scalar solutions to n-dimensional problems. So when you have a like n-dimensional, like, I don't know, huge matrix, whatever, you're gonna end up with numbers that are on the diagonal. And these numbers are very nice because they turn out to be scalar solutions. So they're basically a number over here times the identity matrix. So a bunch of different of these numbers times the identity matrix. And when you multiply that to another matrix, all you have to do is literally just multiply the other matrix by the number itself. So in a lot of problems where you're dealing with high dimensional solutions, you want to get the eigenvalues. So over here, this is kind of a more formalized definition. Letting C be like this matrix, let's just make this like a square matrix, like n by n matrix. Then this minus the identity matrix times the eigenvalue will be 0, which means that these two are functionally equivalent, as long as they're transformed. So what do I mean by transformed? Like these matrices have to be multiplied by something to like turn them into something that they're the same as. So that now let's say you're given dz over dt equals jz, where jz is a matrix, right? We want to transform this such that z equals z0 times e to the jt. Okay, this is literally the given solution here. But then this also will equal z times transform of e to the lambda t. So this is the solution that we're going to be looking for, kind of like the final solution. But this is just more of a overview for generally what you want to do, while we're solving the problem at the bottom, we will naturally arrive at this solution, which is really nice. So let me underscore this. So, okay, now on for all the fun topics. So there are many things you need to know going into this problem in order to solve this. First, let's talk about nilpotent. So nilpotent is a matrix that looks like this. Meaning if you square it, the ones start converging at the top, and then every time you do that, then eventually it becomes 0, so it disappears. So this is good because that you know that there's like some kind of pattern to this, and then if you do the pattern, it breaks at 0. So if you have n to the 0, it's going to be a identity matrix, right? N to the 0 is because anything to the 0 is 1. So you have identity matrix. N to the 2 is going to n is going to be this. Oops, n is going to be that, and then n to the 2 is this. Okay, and then you also need to know the commutative property, which is of course an identity matrix times any matrix can be swapped around, and then lambda is scalar. So this isn't strictly commutative, but it's just some math properties. So these are all equivalent. All right, so now over here we have J is this cool matrix. So as we can see, this you can break them up into two very, very important kinds of matrices. One is the eigenvalue matrix, which is just a bunch of lambdas in diagonal form, as was mentioned previously. And the other is the nilpotent matrix. You can write that as the sum. So we can basically write J equals lambda I plus n. This will become very important later. All right, and then what other things do we need to know? All right, so exponential. Since we're going to be dealing with exponential terms, as you see here, e to the jt, e to the lambda t, we'll probably want to know what it actually means. So here's the definition of an exponential, which is the sum from k to 0 to infinity of x to the k over k exclamation or k factorial. I don't know, I said exclamation. And binomial is also important. So okay, so over here, these two, binomial and pairwise summation, this one you don't need to know from the beginning. These are things that you'll see that you'll need to use, or will be very nice to use as you solve these later. So these aren't obvious from the start in the question, but the other ones are probably more important, and you can see them from the beginning. So why is binomial important? Okay, well, so this actually comes from the definition of J. So over here, you see that over here, you'll see that you have an exponential to the k, right? So so e to the x is x to the k, and you'll have a e to the j over here. So then that means sometimes you might run across something which is going to be like j to the k. So that means you want to use the binomial theorem later to figure this out, or at least to break it into something simpler to solve. Okay, so that's what the binomial is going to be used for, and it's this property. It's pretty straightforward. And then finally, a pairwise summation trick. So over here, if you have a sum to infinity, n equals 0, and then over here a sum to n, or k equals 0, this will be equivalent to you can reparameterize it as sum to infinity k equals 0, and then sum to infinity n equals k. I don't have a formal proof written down for this. This is a big problem of its own. But in essence, you can see it from this picture over here. So over here, you have the sum to infinity from n, and then k is going to be basically from n to infinity. But then this is basically the same, except you're looking sideways now, and it's going to be sum from k to infinity, and then n is going to be from n is going to be k to infinity. Okay, cool. So now that we got everything here, we can finally plug all these in or use all of these to solve our enormous problem over here. Or not enormous, but bigger problem. All right, so over here, e to the jt, we can turn this into the form over here with the exponential. So it's going to be sum, let's just say sum from n to infinity of e to the jt. And then so it's going to be this form. And after that, okay, we got this number down, and now we want to make this actually solvable, or break this down into something we can figure out. So over here, we notice that, okay, well, j is lambda I plus n, so we can put this in, substitute this in, and we got something here. It looks like we're starting to get something, but this lambda I plus n to the n power is going to be very messy to do. So what we want to do is we take this and we apply the binomial theorem to here, and then substitute the binomial version of lambda I plus n to the n with this. Okay, notice that I put lambda to the k and n to the n minus k over here. So straight from just from the get-go, we'll get lambda to the k, which means that we have a eigenvalue to the k, which is a really nice number because we can just basically put that off to the side and basically try to find big N to the power of n minus k later. All right, so and then don't forget there's a 1 over n factorial also. So we can rearrange things to make it look nicer. And what do we have here? Well, we have this thing. And what does this look like? Well, this looks like this over here. And so at first these two terms were coupled in a sense that they're from k to n. But if we substitute this later with k equals 0 to infinity and n equals k to infinity, then we can notice something really interesting. So let's plug that in. Let's also get rid of the factorial. So this term, so binomial term. So this again was going to be n over k, n minus k. And if you have this, then over here you have a 1 over n, then you'll get, you just can cancel out the n factorials and then you'll get these terms. All right, so now that you have these terms over here, you want to be able to find a way to, separate them. And then you know that it's possible because it straight up tells you like you can separate this into e to the lambda t. So which is a really good hint because over here you have something that's not separable, which is t to the n, where n equals k. So how do you separate this? Well, here's like a really interesting thing you could do. You could substitute k, or you can substitute n with m plus k. So over here. So if you do that, then over here, okay, so n, it will be m plus k. So let's just make this m equals k. And what's k? Well, k is going to be n minus m. So n minus m is going to be 0 to infinity. And over here, the rest of these numbers, n minus k is going to be m, n minus k is going to be m, and t equals k plus m. Which is really nice because t is going to be T is a scalar. So instead of having a matrix as the thing that's going to be like multiplied to like a annoying amount, you're going to have a scalar multiplied to a good amount. And that means that you can break this into two parts. So you can have t to the k plus m is basically the same as t to the k times t to the m. So now that you have everything separated, you can put them into their own little groups, and basically the answer is this. So it's sum of 1 over k factorial times lambda k, lambda to the k times t to the k, times sum of 1 over m factorial n to the m times t to the m, which is really nice solution. So all we have to do now is to finally turn this back into a more standard form. So straight from here, this is literally the definition of E. So you can turn this into E to the lambda t for this first part. And then for the second part, it's a little bit more complicated. So let's write this out. Let's write the summation out. We'll get that this is going to be 1 over m exclamation or factorial times n to the m times t to the m. And this is, if we break this up into, let's just say to the first 3 powers, we'll get I, which is going to be this, times nt, n is nilpotent, so over here, so t with 1, and then 1/2 of nilpotent squared, which is going to be 0 with a 1 at the very top corner. And after that, remember, everything becomes 0. And what do we end up with? Well, we end up with this matrix. So finally, you combine everything together, and you'll get that over here, e to the jt, which we were trying to look for in the beginning. E to the jt equals e to the lambda t times this matrix. And then you can plug this in and get z equals z0 times e to the lambda t times this matrix.